Now we're going to focus on some uh, special types of forces. Okay, we've met a couple of them already, but these, I'm just going to get straight into an example and then describe what it is. All right, so take um, this is work done by a spring. So we have a spring, and a mass at the end of the spring. Um, Position x0, and then we stretch it out to position x1, and then again further out to x2. Okay. Now, it's a linear spring, so the force produced by the spring is proportional to the displacement in the opposite direction. And Cartesian coordinates would be given by that. All right, where x is taken to be typically taken to be 0 at the equilibrium point. Like a spring, if you stretch it, the force will be pulling it back towards its equilibrium point, and if you compress it, the force will be pushing it back towards its equilibrium point. So it always has some desired point, and x0 is usually taken to be that equilibrium point. All right, so at x0, if we just leave the spring alone, it won't move. All right, so the force will be 0 at x0, typically. All right, so let's calculate the work done. So the work done from position, say we're going to take the mass from x0 to x1. So the work done from 0 to 1 is equal to that. All right. Well, so what is in Cartesian coordinates? We can break these both down into terms of in terms of x, y, and z. Okay. And in this case, since we only have an I component, this just simplifies down to that, and then we can integrate that simply to be and so the position vector is quantified completely by its change in the x position in this case. Okay. even if it were changing in the y position, for small enough changes, that would have no impact because it wouldn't stretch the spring any. All right. And so the particle is constrained to move in the x direction. This is the only integral that matters, and so we wind up with that relationship. Now, likewise, from position 1 to position 2, now we're going to stretch it further from position 1 to position 2, and that's just the integral from this should be from x0 to x1. Now we're going from x1 to x2. So now this is okay. So we did this much work to stretch the spring from x0 to x1, and then we do this much work to stretch the spring from x1 to x2. So what happens if we well, first let's compute the stretch from 0 to 2, and we just do the appropriate substitution for all the variables here. So x0, x2, and now we can illustrate the fact that the work done to stretch the spring from 0 to 2 is equal to the stretch done, the work done from 0 to 1 plus the stretch or the work done from 1 to 2. Okay, and so u to 0 from 0 to 1 and these x1 terms cancel, and so we're left only with which is u0 to 2. All right. So bottom line is the work done from 0 to 1 plus the work done from 1 to 2 is equal to the total work done from 0 to 1. And the implication there is that the spring is what's called a conservative force. This spring force, defined by this relationship, is called a conservative force. And a force is conservative if the work that it does depends only on the initial and final positions. I.e., the path is independent of the path. All right, so the work from 0 to 2 is equivalent to the work that's required to go from 0 to 1 to 0 to 1 to 0 to 1 to 0 to 2, or 0 to 1, 0 to 1, 0 to 1, 1 to 2, or whatever. If you started at 0 and you wind up at 2, you do the same amount of work depending on, it doesn't even matter how you got there. All right. Now, there's another definition that's implied here, the idea of potential energy. Now, potential energy is it's energy that is that can be stored in the mass, in this case, in an object. Do you see what I'm saying? If I take this object and I move it to x1, I did a certain amount of work, and if I hold it there, there's a certain amount of energy that's stored in the object, and that's evident by when I let go of it, it moves. So there's a bunch of kinetic energy and some complicated interaction here. So I stored energy in it by stretching it out to x1, and then when I released it, that energy is free to do whatever it is that it was directed to do, essentially. And so potential energy can be converted to kinetic energy by allowing the force, the conservative force, or the force, to do work. So I can store the energy in here by doing work onto the spring. I hold it here, and because there's no motion, there's no work being done if I hold it steady at x1. When I let go, clearly what will happen is the mass will start to move. At that instant, it's gaining kinetic energy due to the fact that the spring is doing work on it. So it's converting that potential energy to kinetic energy and vice versa. Of course, it'll overshoot, and there'll be an exchange between kinetic and potential energy. Okay, there's another important type of conservative force that we're going to be dealing with, and that's the gravitational force. All right, so you remember the force of gravity is equal to this right here. We kind of discussed this when we were dealing with space mechanics. But when you're close to the surface of the Earth, R is essentially equal to the radius of the Earth, which is a constant from our point of view, and the radial direction is equal to k, typically, the upward unit vector, right? And so we can write this near the surface of the Earth. Now look at this. So this is an approximation. Clearly it's an approximation. So we have a constant here. We have so negative g m over re squared times the mass of the object times k. And we can group all this together. We call it little g. Okay. All these three quantities are constant, so we can call that little g. We can call it whatever we want to call it. We choose to call it little g. And weight, the weight of the object is defined as this product. It's always directed down. So that's just the weight vector. This is equal to the weight vector. And so if we want to know the work that's done by the gravitational force in this situation, it's equal to and just like we could expand it up here, the only component of consequences in the upward direction, so the k component, and so we get okay, just like we did here. So the work done is a function only of z. The weight is going to be constant, and so the change in elevation is the only thing that plays with the amount of work done. So, and to expand this to like finite quantity, this is equal to and we can take in this situation, so the choices for Z1 and Z2, the only thing that comes into play is the difference. So the work done, or the change in energy, is only related to the difference here. So the choice of which one we choose to be the datum, we usually choose a datum, and in which case is for gravity is usually taken to be the surface of the Earth, or maybe you have some other arbitrary datum like the tabletop or something along those lines, which serves as your 0 point. So we can choose. We're free to choose this, and so we take z2 to be equal to 0. We have a choice when we decide on where to put our coordinate system. We choose z2 to be 0. And so that the work done by the force of gravity to take an object from z1 to 2, to take it from some height to the ground, is a positive quantity, and it's mgz. So we call this the potential function. We call this a potential, the gravitational potential. Okay, subject to the idea that z is measured above some datum, which is usually taken to be the Earth's surface, or some datum that we choose, some convenient datum. And so if we move downward, you notice that the potential energy decreases. So if we take the datum to be the surface of a pond or something, and we submerge ourselves below the surface, we could wind up with a negative potential energy. All right. Now, what does that mean? That means if I have if I elevate an object from the surface of the Earth, say, to like 10 meters, I've accumulated a certain amount of potential energy, which would be released as I let go of the object and be converted to kinetic energy as it falls. So the sense makes sense, right? If z is positive, i.e. I elevated the object, when I let go of it, it will release that potential energy and convert it into kinetic energy. Now the same thing was true for the spring. This is called like the elastic potential energy. And so the work done to move an object from, say, position 1 to position 2 and likewise we can set x2 to be equal to 0, and we arrive at the amount of work it takes, or the amount of work that it takes to move an object from position 1 to position 2, or the amount of work done by this force to move an object from position 1 to position 2. And so we arrive at the potential energy. The elastic potential energy is just so this becomes a positive quantity because of the way we defined it. And because x2 is 0, x is just the distance from the equilibrium position, or whatever we choose to be the datum in this case. So just to write this more concisely. All right. So now we have two potential functions. We have gravitational and elastic potential functions. There's plenty more. There's like electrodynamic sort of potential stuff and things like that, but I think these will probably wind up being the main ones we deal with. I'll be surprised if we ever see anything else, and if we do, I'll have to be very explicit in how we define the potential functions and whatnot. But so these are potential functions. And they are a consequence. See, they're just a function of position only. So they are a consequence of the fact that these forces were conservative. Okay, and so conservative forces imply the existence of potential functions. And potential functions really just sort of they quantify the potential energy. All right, so gravity near the Earth's surface. This is also true. I mean, gravity is a conservative function in space as well. So the more general case that we discussed earlier is also leads to a gravitational potential function. but for close to the Earth, it's given by this. And then in the case of springs, okay, now it's also true that the work done from, say, position 1 to position 2 is equal to the change in potential energy um, when moving from position 1 to position 2. Okay, and then when released, so if I take our spring, in the instance of our spring, if I take my spring and I take our object and I exceed it out to x1, it acquires a certain amount of potential energy and 0 kinetic energy, say. Then I release it. The work that I put into it from 0 to 1 is going to be equal to the kinetic energy it acquires as it returns back to its original position. And so another way of saying that, and I mean, it should be clear from the way I wrote this stuff, is that that's going to be equal to the change in kinetic energy when going back from 2 to 1. So I go from 1 to 2, I input some potential energy. When I release it, it'll be equal to the difference in the kinetic energy between the two as well. And so I can rearrange this so that V1 plus T1 is equal to V2 plus T2. This relationship is called the conservation of mechanical energy. This isn't the conservation of total energy, really, because of the fact that we assumed that the forces involved here were all conservative. Okay, so the sum of potential and kinetic energy is conserved when so this is, if the forces acting on the object are conservative, then this is what we meant by a conservative force. This combination of, or the sum of the potential and kinetic energy is conserved. So what is a non-conservative force? Well, the primary example is friction. Or air resistance, maybe? Or something along those lines. So really it's friction. Fundamentally it's friction. Air resistance is just a special form of friction. But you know what friction does? Friction takes some of that kinetic energy and converts it to heat, which is another form of energy that we're not going to be studying in this course. So we treat it as if it's just lost energy. All right. It converts it to heat. That heat is not useful to us. It's neither potential nor kinetic energy. And so the full conservation of energy is, say, would be something like that. So if you can account for that lost mechanical energy in the form of heat or something along those lines, then this would be like the full conservation of energy. You have to account for that energy that's converted into by some other means. There's all kinds of energy, right? Kinetic energy, or I'm sorry, chemical energy, nuclear energy, electromagnetic energy. Like, there's all kinds of energy that we're not going to be dealing with. But if we were considering all those things, they would have to be brought into account here. Fundamentally, all of those things are just different forms of potential and kinetic energy. Like, what is heat if not? It's just disorganized kinetic energy at the level of the molecules is all it is. Okay. And then there's another fact. Potential functions can be added. So maybe we have an object that's under the influence of both a spring and gravity. So then the total potential energy of the object is equal to the sum of the gravitational potential energy at the same position plus the elastic potential energy at that same position. Okay. And so as you change position, you can keep account for this sum, and the same relationship applies. So you can add potential energies is the only upshot here. And there's another interesting fact that the force can be recovered. If the potential energy is known, the force can be recovered by taking the negative gradient of the potential. So the potential function is a scalar function. It just gives a number. Like, energy is just a number, see? Like, if I plug it in x here, I get a number. I don't get a vector. So it's just a number. And if I take the gradient of that function, the negative gradient of that function recovers for me the force that's acting on the object. All right, so for this operator, the gradient operator is equal to, in Cartesian coordinates, the derivative with respect to x times the I vector. It has different definition in different coordinate systems, so be careful. And this is in Cartesian coordinates. And for gravity, just for completeness, I want to write this out. So if the Vg is mgz, right? That's the function that gives me the potential for gravity. So I'm going to take the derivative with respect to x of mgz times the I vector plus the derivative with respect to y of mgz times the j vector, and then derivative with respect to z of mgz times the k vector. Well, that's going to be 0, that's going to be 0, and so this is just mg times the k vector, right? So the derivative of mgz with respect to x is 0 because there's no x involved. Likewise for y. So the only thing that matters is mg's, the z derivative, and that is equal to that. And so the force of gravity is equal to the negative of the gradient, and that checks, right? And then likewise for springs, the gradient of the elastic potential is equal to it only involves x, so this is the only component. This is going to be the only component of importance, and so this just equals to that, and then so the elastic force is just now it isn't always in the I direction, right? If the spring is hanging vertically, clearly it's not going to be in the I direction. I just you'll see this in the examples, okay? So sometimes these forces can change directions, depends on what orientation for your coordinate system you chose. All right.